or graphical plot between composition and temperature. These graphs are drawn by way of varying the composition and heating the alloy to the closer above the melting point and then cooling at various temperatures and measuring the change in the phase from solid from liquid to solid, and then noting down the various points on the graph. So in this way the transformation of phases are recorded at various temperatures, and the horizontal line in the phase diagram is identified as the isothermal line. This phase diagram is a isomorphous system, isomorphous phase diagram. This phase diagram is copper nickel phase diagram. This is a best example for substitution solid solution strengthening system. In this phase diagram, the composition is plotted along the x-axis. This system is a binary system. In this system, copper is marked at the left hand side, and the nickel is plotted on the right hand side. So the composition of copper decreases from left to right, and the composition of the copper increases from right to left. The composition of the copper decreases from left to right, and the composition of the nickel decreases from right to left. So here it is 100% nickel, here it is 100% copper. So the melting point of copper is 1085 degrees centigrade, and the melting point of nickel is 1440 degrees centigrade. So the phase diagram is drawn by heating the alloy. For example, alloy having 40% copper and 60% nickel is heated above this temperature 1280 degrees centigrade, so that it is completely transformed to liquid metal. From this liquid state it is cooled, so that at 1280 degrees centigrade it is cooled, and below this temperature a liquid and solid phase exists. And this state continues up to 1235 degrees centigrade, and at this point it is completely transformed to solid state. Below this line is known as solidus line. Below this solidus line you may find only solid phase, and the solid phase is alpha phase, because this is an isomorphous system, and after solidification this particular combination of CuNi gives a single phase only. Okay. Whatever amount of copper in nickel added gives only alpha phase, a single phase. Similarly, whatever amount of nickel added in copper gives the same phase, alpha phase. That is the salient point of isomorphous phase diagram. So similarly, you can vary the composition by reducing the nickel content. It can be reduced up to say 40%. So 60% copper is present in this alloy, 60-40, and once again this alloy is heated up to the liquid state, and then it is cooled. So the transformation, that is the start of the solid phase formation and the completion of the solid transformation is recorded, and these extreme points are noted for the various alloy combination. Thus this graphical plot is obtained between the extremities of the melting points of copper and nickel. So see in this diagram, here for example, say we can take the 50% copper and 50% nickel alloy system. So this is a binary phase diagram. We call it as binary phase diagram because it has two constituent elements. One is copper and nickel. So in this system, the copper in this system, the melting of the alloy takes place at about roughly 1250 degrees centigrade, and it is completed at nearly 1200 degrees centigrade. So as the alloy content increases, the melting point differs, because the nickel has more melting point. That's why the melting takes place at higher temperature. On the other hand, if you add more copper and less amount of nickel, melting takes place at lower temperature. From this diagram you can note this. So this particular system, in this case, you can find a single phase, that is the copper is having FCC crystal lattice. Similarly, nickel is also having FCC crystal structure, and these two elements are added in any amount. Say if you add 80% copper and 20% nickel, the total alloy content is 100%. So the transform product will be having alpha structure only, that is FCC structure only. The same way, if you add say 50% copper and 50% nickel, once again we will be having phase having 50% copper and 50% nickel, and the crystal structure is alpha only. You will not get any other structure at room temperature or below the solidus line. So this particular alloy, cupro-nickel, is a best example for solid solution strengthened alloy system. So if you look into this phase diagram, we can estimate the amount of liquid phase at this point by way of applying the lever rule. Say we have to draw a tie line. The extreme point of the tie line intersects the liquidous line at R, and the other point, edge intersects the solidus line at Q. This tie line is drawn parallel to the composition line, to the x-axis, and you have, say, at what point you have to measure the composition is the pivot point, which is marked as C0, and this is the Cl and this is the Cs, and the composition of the liquid phase, the composition of the solid phase, and here I have shown the tie line, and here this is the pivot, and here this R point at which the fraction of liquid phase is measured and fraction of solid phase is measured at Q, and is marked as C suffix L or C suffix L and C suffix S. And while applying lever rule, to measure the fraction of liquid phase, you have to take the distance between the pivot and the solid side length, that is P and Q, divided by QR, that is CS minus C0 divided by CS minus C0, that is the length of the PQ segment, divided by CS minus CL, that is total length of the segment, the segment which is QR. So PQ divided by QR, that gives the fraction of liquid phase. We know very well that the fraction liquid plus fraction solid is equal to 1%. That is the 1, and that is 1, not 1%, 1. So weight percentage of solid phase is equal to 1 minus FL. The weight percentage of solid phase can be measured or calculated using this formula, C0 minus CL by CS minus CL. For this, you have to apply this simple rule. Say here is the fraction solid, so the opposite to this point, what is this? This RP divided by QR, that is the total length of the line, the segment RQ, right, RQR. So RP by QR, that gives the weight fraction of solid phase. So the reaction, the isothermal reaction is represented here. The liquid upon cooling transforms to single solid. Upon heating, it transforms, the solid transforms to liquid. This is the isomorphous phase diagram.